Today's section, Preview Transformations, comes from section 2.7 in the textbook. We will be taking several different functions and transforming them. So let's do a quick review of some of the transformations. Remember that a transformation of a function is an alteration of the function rule, which results in an alteration of its graph. So taking one function and moving it. Moving it could mean a translation, slide, vertical stretch or compression. We could stretch it vertically, or we could smash together, compress it. Same thing horizontally, and then we also have the reflections over the different axes and lines. We could also combine these four different types of transformations. So I have down, memorize them, start with them now, you'll catch on to them. They will be repeated throughout the course using different equations and different functions, but they'll always be the same transformations. So if you can work on them now, get them memorized, what goes with what. So let's look at them individually. Let's start with the translations. If, you'll notice, if you have a function, then you have the same function with a component added to it, like k. This would give us a vertical translation of the graph. It would move up or down. Now notice, the translation is k units up if k is greater than 0, and the absolute value of k units down for k less than 0. So if k is positive, it moves up. If k is negative, it moves down. Notice the k is outside of the function. So you would see the function and then you would have this component added to it. Whereas in the second example, if y equals f of x, then y equals f of x minus h, the actual subtraction, addition, combination is inside along with the function. This gives a horizontal translation of the graph. Notice inside, think of it x-axis. X-axis, you move horizontally. So if it's in the parentheses with your values, then you're going to move horizontally. The translation is h units to the right if h is positive, and the absolute value of h units left for h being negative. So now, with your graphing calculator, let's start with, you should be able to graph the function f of x equals the absolute value of x. Follow that with the second function of g of x equals the absolute value of x minus 3. And then with the third function, h of x equals the absolute value of x plus 3. So as you're graphing that, you should be thinking, hey, these are of situation 1. Because there is the function there, the absolute value of x, which was the original function. So if we want to say this is the original, and from here, then we moved it to a minus 3, subtract 3, and then we had a plus 3. So really the only difference is that portion right there on both of them. And if you look back at the original, if you have a k value, that k value will give you a vertical translation. If k is positive, which we have here, it should be up. And if it's a negative value, then it should be down. So check your graph. And did you get that we would have a vertical translation 3 units down for the first one, and a vertical translation of 3 units up for the second one. Then clear things off and start again. Two new functions. F of x equals x squared will now be the original function. And g of x equals the quantity x plus 2 squared will be the second. And h of x equals the quantity of x minus 2 squared. So we're seeing something happening inside of our rule. So this used to be in the original form x squared. Well, now we have x plus 2. And over here in its original form, it was x squared. Now it's x minus 2, the quantity squared. So think about what you should be anticipating for seeing on your graph based on what we discussed. And the translation is h units to the right if it's greater, so we should have 2 units to the right for our first one, and it should be 2 units left for the second. I don't know, here it is. Second graph, horizontal translation, 2 units to the left, otherwise 2 units to the right. So, make sure you have seen all of them, and you should have the original, then you have g of x, and then you have h of x. Next one, translations. Done. Vertical stretch and compression. Look at the original setup. So we have if f of x is our function, then we have a multiplier out front of that function. So this is the new piece. It gives a vertical stretch or a vertical compression of the graph of f. If a, the value you're multiplying by, is greater than 1, the graph is stretched vertically, pulled by a factor of that a value. If that a value is between 0 and 1, the graph is compressed vertically, smashed together, shrunk. Now notice that they don't talk about the value of 1 at all. But if you think about it, if a is 1 and you're multiplying any function by 1, what's going to happen to it? That's why 1 is not included in the restrictions. So if you look at these, based on what we just talked about, look at the original. So here's our original, f of x, and compare it to our new function. What you're seeing is the 3 halves is the only thing that has changed. As is also, again, down here, f of x is your original, and the new piece is the 2/3. So with that, you can see 3 halves is a number bigger than 1, 2/3 is a number less than 1. What should you be expecting to see if you have a graph? You should see a vertical stretch by a factor of 3 halves. Down here, you should see a vertical compression by a factor of 2/3. Vertical stretching compression. The a value is in front of your function. Next one, horizontal stretch or compression. Notice the original, if y equals f of x, and then y equals f of b of x, it will give a horizontal stretch or a horizontal compression. Notice the factor again, b is contained in the x. So think again, x-axis, if it's inside with the x, we're doing something along the x-axis. And so our values are if b is greater than 1, so if that thing we're multiplying is greater than 1, the graph is compressed horizontally by a factor of, here's the hard part, 1 over b. If it's compressed, think of it as getting smaller, shrunk, so it's going to be not as big as it was originally, so a fractional answer. So if b is greater than 1, it will be horizontally compressed by a factor of 1 over b. If b is between 0 and 1, the graph will be stretched horizontally by a factor of 1 over b. So if we had 1/2 as our b value, the graph is stretched by a factor of 1 over 1/2. 1 divided by 1/2 is the same as 2. And again, in the restrictions, 1 is not looked at because it will not change the two graphs. So it's not included in the restrictions. So again, looking at some functions here, if we call f of x our original in both cases, the piece you're seeing different is what is being multiplied by x. So this is the only new piece. Down in this one. And so you should be able to say, wait a minute, they're identical except for that multiplier on x inside the function. That's what we have here, the multiplier on x. So you should be able to tell me how it's been horizontally stretched, compressed, accordingly. So if you have yours done, double check. This first one is a horizontal compression by a factor of 2/3, because remember it's 1.5 over, or 1 over 1.5. And down here, it'll be a horizontal stretch by a factor of 3/2, again because it's 1 divided by 2/3. That leaves our reflections. Notice in the reflection, if you have your function, and then you have the opposite, or you could say a multiplier that's a negative out front. A -1 is all we need. So here is the new piece. That negative sign. Opposite of our function. It gives a reflection of the graph of f across the x-axis. If y equals f of x is our original graph, and the negative sign is in with the x included, that will give us a reflection of the graph across the y-axis. So think reflection, it's in with the x, something's happening on the axes, but the only way you can fold if you're on the x-axis is left and right to get us to that graph that would fold, reflect across the y-axis. So looking at your examples, again we have the f of x function we're calling the original, same one we used before. And now the only difference is you see out front a negative value. Everything else is the same. So it should give us a reflection of the graph across the x-axis. Then we have the graph of f of x. This is our original. Look at it carefully and compare to the next one. The only difference is the x value is now negative. It's a negative x, so that should give us a reflection of the graph across the y-axis. Double check to make sure that's what you have, and you should be good to go. Now, last but not least, what if we do some combining? Any of those, all of those could be combined. We could have 1, 2, 3, or more all in one equation. So you're really going to have to compare the equations and see what you have, and then go with, hopefully, your memorized versions of what changes. So, graph each pair of functions and identify the transformations from f to g. So you can see our original is a simple f of x equation. Now, when you come over here, you can say, wait a minute, we've got something happening here, so we've got to add 2 in with the x, and then also we have this -1 outside. So you got to be thinking something's happening. Now, you could always graph it, but what if we don't give you a grapher? That's why we need you to start memorizing what's going to happen. It's going to be so much quicker for you to anticipate what's going to happen. So what kind of move did you see? Would you see if you didn't graph it? We have a positive value in being added and subtracted with the x, and then we have a minus -1 outside. So ask yourself, or graph if you're still working on memorizing them. Did you get over a horizontal translation 2 to the left and a vertical translation down 1? So we will talk more about these and any issues you may have had with your calculators when we come to class. But again, work on memorizing the different outcomes. That'll be best because, as I said before, we will be working on them throughout the year in different scenarios. That's all for today.